All right. So we had just finished the discussion on internal flows and only flow. Now what happened is, what we will do is we will now extend our discussion to force convection for internal flows. Okay. Now,
Said you did not share your screen.
oh, I have not shared my screen. Correct. Thank you. Thank you for pointing out. Okay. This is force convection, internal flows. So what happens here? If you think about it, in the first case, there are, I would say, two, which you already know, two basic boundary conditions. Okay, what are those? One is isothermal and the other is isoflux. It's the same whatever we have seen before as well. Okay. In isothermal, what happens? I'll draw, let us say, a tube. Okay. Well, I'll draw the same for isoflux as well. What is the difference? In isothermal, this T wall, this T wall is constant. Okay. Let us say it is like 90 degrees. Okay. I have flow coming in at U infinity. And let us say at the inlet, the TF of the fluid, TFI, is 30 degrees. Then what will happen slowly? This fluid, because it is at a lower temperature, there will be heat transfer from the wall to the fluid. Right? The fluid temperature will keep increasing. Great. The fluid temperature keeps increasing. Increasing to what? So let us say it's 30 degrees here, maybe somewhere here it is 45, maybe 60. Okay, 80. And then finally, TFE will be is less than 90 degrees. It is possible theoretically just to reach 90 degrees. If it reaches 90 degrees, it means after that there will be no heat transfer because the fluid is at the same temperature as that of the wall. So therefore, there will be no heat transfer. Okay. So if I have to draw this now for isothermal, once again, how will the temperature profile look like? That's important, right? Correct? So let's try to do that. What we are talking about, this 30, 60, this is the mean temperature of the fluid. But there will be locally a temperature variation in the radial direction, right? Because the temperature of the fluid will be, I mean, right, the layer of molecules which is clinging to the surface will be at 90 degrees and then slowly it will come down. That's the thermal boundary layer that we know. Okay. So how will the temperature profile look like of the fluid, that is? At the inlet, it's all uniform. So let me draw the center line. It helps to draw. Okay. Then what happens? After a while, let us say this is 90. After a while, the temperature changes like this. Okay? Because the thermal boundary layer is growing. Within the thermal boundary layer, the temperature changes from the wall temperature to the inlet or free stream fluid temperature. Okay, and beyond the boundary layer, the effect of the high temperature at the wall is not felt. I go further. What will happen? The wall temperature remains the same. So let us say maybe somewhere here again. But what happened? The fluid temperature keeps increasing, and at some point, the flow becomes fully developed, which means the effect of the high temperature at the wall is penetrates right into the center line. The thermal boundary layers merge, and you have fully developed flow. Okay. Now thereafter, what happens is unlike fully developed flow and velocity profile, the temperature profile keeps changing. How? Because there is heat transfer. The fluid will keep heating up. So therefore, after a while, the wall temperature again remains the same. So let us say it starts again at 90. But the difference between the wall and the fluid temperature will keep reducing. Okay. And somewhere you are going to find a profile like this. Okay. So let us write it down quickly, what we just discussed. So these are things that we are not doing mathematics. These are just based on your fundamental understanding. We can predict these. What will be the profile? What will be exactly? How much is the temperature rise, etc. Yeah, for that we need to do some calculations. But at least the qualitative trends, just from our knowledge, understanding, and intuition, we can predict. Okay. So fluid temperature increases at the wall. Okay. For short distances, it does not reach the internal core. So the flat region at the center equal to the inlet temperature. True? Agree? So again, once still here we know that this is developing and this is fully developed. Okay. After a distance, and when I say distance, this is along the streamwise direction. The effect of heated wall penetrates till the center line, and this implies fully developed flow, right? Further downstream, temperature difference between the wall and fluid core temperatures false, right? That's exactly what we saw. All right. Now let's do the same for the isoflux condition. In isoflux condition, the thing is that you are supplying a constant heat flux. And again, remember, this is an easier boundary condition to realize practically. I can just wrap a heater around the walls and just use resistive heating, pass a current through the heater coil, and I'm going to get uniform heat flux. Okay, so over here what happens is Q double prime at the W is constant. Right? So what happens over here is the temperature of the wall is not constant. We don't know. Okay. Fluid likewise will come in and it will get heated, but the wall will also get heated. Okay. Why? Probably you know, but we will see that. So let us see what is happening here. Similarly, at the entry, this is how the fluid temperature is. Slightly inside, still developing. Then it becomes fully developed. And let us say it is like this. Look here, one thing. The wall temperature over here was constant, but over here is not. Okay. What will happen hereafter? So this before telling you what will happen, let us try to predict what is going to happen. And this I will directly do some calculations. I'll write an equation right away first. I've said that my QW prime wall is constant. And what is that? That is H times Z times T wall Z minus T fluid mean of Z. Okay. Now what happens is the wall temperature, we will see later that the heat transfer coefficient actually is constant for fully developed flow. We're not going to derive it. So if heat transfer coefficient is constant, then if my fluid mean temperature increases, my wall temperature also has to increase. Not only that, it will increase such that the difference between wall and fluid temperature remains constant. Okay? So wall temperature increases with Z. Okay? The same thing at the beginning, there is no photo, so I'm not writing all these here again. Flow develops to fully developed flow. Okay? At fully developed flow, the wall and fluid temperatures will keep increasing with constant difference. Guys, please keep this in mind. Okay? Or TWZ minus TFZ is constant. All right. So the last thing I'm going to do for both of these is let us try to draw the temperature profiles. This is Z, this is temperature. Okay. See, for the wall, for isothermal, sorry, my wall temperature is constant. And what happens to my fluid temperature? Okay, let us say this is the transition from entry region to developed region. The fluid temperature, it starts from somewhere TFI, and then it keeps increasing. Going towards. Okay, this is my TF as a function of Z, TFM rather, the mean temperature, right? Across the cross section. But within the cross section, again, the temperature is changing, right? From maximum at the wall to the minimum at the center line. All right, so this is also called the bulk mean temperature of the fluid at that cross section. Okay. And finally, please draw this now, and we will come to the explanation later. I'm drawing this right now because I may be deleting them later or what. So I'm drawing one more curve here. And this actually is your heat transfer coefficient variation. And as you can see, the heat transfer coefficient for fully developed flow does not change. is constant. So we'll come to this later when we look at correlations, etc. But keep this in mind. Similarly, if I have to draw the same thing over here for isoflux, it will look very similar. This is Z, this is T. Okay. For isoflux, okay, let me again draw this. For isoflux, the fluid temperature, once again, it starts from TFI. And it increases linearly. Okay. Keep that in mind. TFM Z increases linearly. And it's very easy. Why? Because, as we will see later, because the heat flux is constant, we'll just derive it right after this. Because the heat flux is constant, then what happens? Q double prime times the perimeter times the length. That's the total amount of heat. That is equal to m dot Cp delta T. And delta T is TFMZ minus TFI. Okay. Because, again, I can probably write it here. Q double prime times the circumference times Z is equal to m dot Cp right. So that is why this increases linearly. Okay. If this increases linearly, and I have told you already without proof that the heat transfer coefficient in fully developed flow remains constant. Okay. So let me draw that again here. If the heat transfer coefficient remains constant and my heat flux also remains constant, then it means my temperature difference between the wall and the fluid mean temperature also has to remain constant. Why? Because of this equation that I had written right here. If Q is constant and H is constant, this difference has to be constant. So what does it mean? In the fully developed region, my wall temperature will also vary linearly. Okay. In the entry region, however, what happens? I mean, look at just the entry point. Both the fluid and the solid are at the same temperature, right? This is a singularity point, of course. This is also TF, this is also TFI, this is also TFI. So which means my heat transfer coefficient is infinity. If the heat transfer coefficient is infinity, which means the distance between my wall and the fluid has to be 0. Or other way actually, so it is 0 here. And then what happens is the wall heats up. In the developing region, of course, the wall heats up at a higher rate and finally reaches this. Okay, so please keep these graphs have a photographic memory of these graphs. If you remember this, everything becomes very easy. Think about this. I'll give you about 30 seconds. Look at these curves. Except for heat transfer coefficient, just convince yourself that you understand these variations and agree with it. Okay. Any questions?
So can you please explain the temperature of the wall in the developing flow for the
Temperature of the
isoflux
wall.
condition?
Okay.
Yes.
Okay. So as I said, the heat transfer coefficient remains constant, right, in fully developed flow. Okay. So if heat transfer coefficient remains constant, my Q double prime at the wall is what? My H times correct? That is how heat transfer coefficient is defined, right? That it is Q double prime is heat flux is heat transfer coefficient times the temperature difference between the wall and the fluid temperature. And in this case, what is the fluid temperature? For flat plate, we take it to be the free stream temperature. In this case, we'll take it to be the mean temperature. Okay. So now, therefore, TWZ is TFM Z plus Q double prime over H Z, right? Sorry, Q double prime W. So Q double prime W and H Z are constants. So therefore, the wall temperature will be the fluid temperature plus some delta. And since the fluid temperature increases linearly, the wall temperature also has to increase linearly. And this difference, this delta T, is Q double prime over H. Okay. However, at the entrance region or the developing region, the entrance and developing are the same. They mean the same. Entrance, entry length, entrance region, all that there. For the developing zone, developing range, all that stuff. They're all just the same thing, different names of the same thing. At the entrance region, at the beginning, I have not started heating, right? It's just getting heated up. So the temperature at the entry point will be equal to that of the ambient. Ideally, okay. In reality, of course, there will be some spreading. The wall will have some finite conductivity, all that stuff. So it will never be like that. But theoretically, the temperature of the wall and the fluid is the same at the entry point. And since there is some heat flux, it means that the heat transfer coefficient will be infinity. Right? You can also think about it in this manner. Even for flow over a flat plate, right at the leading edge, my boundary layer thickness is 0. My thermal boundary layer thickness is also 0. Right? See, the thermal boundary layer thickness is 0, which means there is no resistance, and therefore heat transfer coefficient is infinity locally, just at that point. That's a boundary. That's an assumption, by the way, that you don't see that in reality. You see some very high value, but definitely not infinity. Okay. But theoretically, it is infinity, and after that, definitely you're supplying heat, so the wall will be heated up. So there will be some temperature difference between the two, and therefore my heat transfer coefficient will come down. Okay. As the temperature difference between the two goes up in the entry region, my heat transfer coefficient comes down because it has to satisfy this equation, right? Then slowly when it becomes fully developed, then the heat transfer coefficient remains constant. Okay. So far, is it okay? Is it clear, Vatsalya?
Sir, is it linear in the entrance region?
No, no,
The
it is
wall.
not linear. No, it cannot be, right? It has to, the difference has to start from 0. Oh, you mean this, whether this slope is linear? No, 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 this is gradual. Okay. So what you're trying to say is whether this is one straight line at a certain slope and then another straight line. No, this is gradual. Everything is gradual. Now, why is it? So now let me tell you at least qualitatively why the heat transfer coefficient is very high at the entry and then comes down and becomes constant. That value you have already guessed. That is because of this boundary layer, because of the thermal boundary layer. Like if I just draw it over here, at the entrance region, thermal boundary layer thickness is increasing. Okay, therefore thermal boundary layer, remember, is a thermal resistance, is a resistance to the heat flow. So therefore, that resistance keeps increasing, and therefore my heat transfer coefficient will go down. That is true. Okay, we saw that heat transfer coefficient keeps going down with increase in boundary layer thickness. But then, at fully developed region, there is no further growth of the thermal boundary layer, right? The boundary layers have already overlapped, and there is no further growth because it's restricted. So therefore, heat transfer coefficient also does not change. Okay. Now you may ask, what happens here? And let me ask you that. For isoflux case, probably we can, both mathematically and physically, we can tell about this. But for isothermal case, if I ask you from whatever we have discussed, what happens to the heat transfer or heat flux at the wall? How does heat flux Q double prime Z vary with Z? What would you see? The question is, can you plot qualitatively Q double prime Z on this curve? If so, how will it look? Yeah, go ahead. I thought somebody was trying to answer.
Sir, it will decrease.
चलो चलो अगर गलत हुआ तो ठीक है, कोई प्रॉब्लम नहीं है. हाँ बोलो.
Sir, it should keep decreasing alongside.
Huh? Can you repeat? Your voice is cracking.
It should keep decreasing alongside.
It should keep decreasing along Z. Very good. Why?
Sir, because the temperature difference is decreasing. And in fluid flow, heat transfer coefficient is constant, but temperature difference is decreasing.
Okay. Am I back? I think I lost it momentarily. But can you guys hear me?
Yes, sir.
Okay. Yes, absolutely. Very nice. Very nice. So Q double prime Z decreases in fully developed region because T wall minus TFM Z decreases and Hz is constant. Keep this in mind. All right, very good. Looks like at least the basic qualitative trends, etc., are well understood. So let us now do some maths then. Okay. See, I keep repeating. Of course, if you open your heat transfer books, etc., you will see a lot of derivations, scaling analysis, etc., derivation of these correlations. And those are, I'm not saying they're not important, but at the end of the day, for an engineer, for a practicing engineer, convection is largely a correlation based subject. Okay, we can do a lot of analysis on simplified geometries. We do that, and those all have their values. But given the short time, I am not going to focus on those. Those are derivations. You guys are all smart enough. At any point of time, if your concepts and fundamentals are well understood, you can pick up any book or go to any online lecture or online resource, and you can get those derivations and understand them as well. Okay. I'll focus more on giving you the look and feel of the subject. Okay. So let us do some generic formulations and write this. Total convective heat transfer. After this discussion that we just had, this will be very elementary to you. Okay. Q convection, which I'm also going to write as Q, is m dot Cp. This is the total heat transfer, TFE minus TFI. Okay. So if I say that, if that is actually when we do experiments, this is a very good way of finding out. Let us say I'm doing an experiment of fluid flow or force convection for flow through a tube. Okay. So all this we can write that, okay, the fluid temperature increases like this, etc., etc. But finally, I cannot put an infinite number of thermocouples in my tube, right? It is going to disturb the flow. So what we typically do is, in order to find out how much heat has been dissipated, one of the by convection, a check that we do is we measure the temperature of the fluid at the inlet, we measure it at the outlet, we measure the flow rate, and knowing the specific heat, we can say that this is the amount of heat that the fluid has dissipated, has extracted from the heated surface and rejected. So this, even though this sounds very elementary, it's an extremely important relation. And ask any experimentalist, this is the first validation that we do. Okay. To give you another practical example, I'm going to heat the wall of the pipe, right? Yes, I'm going to heat the wall of the pipe. Very good. And then what do I do at the wall? If I heat it, there will be heat loss both to the fluid flowing inside the pipe as well as outside, right? Okay. Then what? Then you would say, okay, well, put some insulation around the pipe so that there is no heat loss to the outside. Yeah, I will put insulation. Definitely, we do, but there will still be some heat loss. Correct. So how do I know how much is the heat loss? This is another way. The total amount of heat that I'm putting in is Q double prime times the total wall area. That is Q input, and this is Q convection, m dot Cpt, the delta T of the fluid. The difference between the two helps us estimate how much is the heat loss. Okay, this is also routinely done. Okay, so a little bit of digression, but what I wanted to tell you is this is very important and we use it so much. Okay. So now let us take over This is my Z direction, having flow, all that stuff. Let us take a very small flow length dz. So over an elemental length dz, I can write dq convection is equal to q double prime times the circumference. C is the perimeter or circumference. Agree? This is also equal to m dot Cp the temperature change of the fluid, the mean bulk mean temperature change of the fluid. Okay, so, or dTf dz q double prime times C divided by m dot Cp. Okay, and what is q double prime again? I can write it as C divided by m dot Cp times H at Z times Tw Z minus Tfm Z. Okay. So the first thing is, as you can see, just 1 minute. Huh? Okay, it's already 9 o'clock. So let's take a break now and we will come back after 5 minutes. Okay, thank you.